Okay, welcome back to Deep Learning Assistance algorithm implementation. So, hello everyone, we are getting close to the last lecture. So in this lecture, we're going to do an implementation lecture on walking through some of the implementation content of the machine learning compilation techniques we talked about in the last week. Of course, it's going to be a lot of those contents are adapted from the tutorials of Apache TVM. So if you want to learn more about TVM related topics, you're more than welcome to check tvm.apache.org. There's another website called moc.ai moc.ai that contains tutorials around machine learning compilation and some of the latest developments. So if you're interested, you should also go and check out that website as well. So to begin with, we will try to obtain a version of TVM. In Colab, we're going to use this pipping store TLC pack nightly. So this package that compiles some of the latest developments of TVM. And we're going to use this as demonstration purposes. So in the last lecture, we talked about the ability to be able to create a loop level program and run transformations of the loop level program so that they could correspond to different performers. And one of the things we are going to do now is we're going to go and try to build a loop level program from what we call a domain specific language in here. So in this code block, what they try to do is we'll try to create a computation that contains A and B are two input vectors, and C is the resulting factor. And in here, we're trying to add two vectors of length 128 together, and the computation is being described in here. And then we are going to call this create prime function to get to the overall functions, and finally, create a module that puts the corresponding function onto it. So let's see, what the result code looks like. So this is a code that is being presented in a format called TVM script, and it represents the corresponding computation that we have on this original computation described. So if we look at the original code, you can find that we're trying to create a function with A, B, and C as parameters, right? So in this case, you can find that this particular function contains A, B, and C as three parameters in here. And the goal here is we'll try to be able to create a set of loops that takes in the data from A and B and tries to do additions and write onto C. So the particular code is this is a pseudocode that looks quite like Python. In this case, we will have iterations over a length of 128. This format is called tensor, so there will be some special annotations of particular blocks of computation. And in this case, we are trying to effectively take I0, assign I0 to I, and then we're running computation of Ci equals Ai plus Bi. Okay, so this is the loop level program that we use to be able to build up the computation that takes in two data and try to store that onto the C array in here. So once we have this called loop level programs, one thing we can do is we will be able to take that R module and try to generate a runnable function by calling build. So in this case, we can call what we call tvm.build by passing that R module and a target. In this case, we are using LVM, which allows us to be able to generate an efficient CPU targeting here. And it's going to return me a runtime module in here. And this runtime module is going to contain a set of runnable functions. So in this case, I'm going to do function equals rt module.main, because if you look at original code, this function is called main, right? It's supposed to take in three things, A and B and C. And what it's going to do is going to read from A and B and write onto C with this computing logics in here. And hopefully, I'm going to pause a bit. Everybody gets what's going on, right? So we have this original program that's being represented as this loop level IRs that contains 3 inputs and a for loop to compute, take the inputs, compute to the output. And then what we can do is we'll call a build to get a runnable function, and this is a function that we're going to invoke. So this is a function called pack function. That is a special runtime function that TVM supports. So it is a function that's used to back the final result of the compilation in here. Once we have this pack function, once we can do is we can try to create arrays and start to invoke computation of arrays in here. So for example, I could be able to create A and B. I'm going to create a C. So in this case, C is the empty array. So C can be arbitrary. So let's take a look A. We take a look A. You can find A is A range, 128, and B is an array that contains all the elements 1. And if I'm going to look at C array now, you'll find that it's quite random, right? This is because effectively we're creating empty array from an empty memory region, and that particular memory region can correspond to any of the data content that you might look like. Okay. So now, once we have those arrays, what we can do is we can go ahead and pass in. We can try to call that function. So effectively, we can call this function passing A and B and C. So what's going to happen is it's going to invoke that particular compile function that we have. So in this case, this particular function describes A, B, and C, and it's going to run this particular computation in here. So when we call this function, effectively, we are passing in, right, the array A to here, array B to here, and array C to here, and it's going to read data from A and B and writes on to C. So supposedly after we invoke that particular function, the result, the C array is going to contain a final computed result. Okay. So let's go and take a look in here. You can find in this case, A corresponds to 0, 1, 2, 3, 4, B corresponds to all ones, and C corresponds to the final computed result, right? So it's kind of our first experience of trying to take a loop level program being represented in our IR module, build that, and then invoke the corresponding function using arrays. You can find that overall process is pretty simple in some sense, right? We build IR module that contains a function definition. You obtain that function in here, and then once you obtain that function, you allocate the corresponding arrays, and you do the corresponding invocation of function ABC that gives you the final result in here. Okay. So this is the basic approach that allows us to be able to start, I would say, take a program and trying to be able to take a program and trying to be able to build and run it, right? On the other hand, what's been more interesting is for us to be able to take a program and trying to transform it a bit. And in order to do that, let's create an instance called schedule. And the schedule is a helper function, helper class that allows us to run transformations on the code. So we know that our original IR module in here can be seen as this is original code, right? And one of the things we want to do is want to be able to, do some loop transformations. Specifically, one thing we can do is we can try to split that loop I. So in order to do that, the first thing I want to do is I will kind of try to get a block that allows me to do s get blocks. In this case, C. It's going to give me a block in here. I'm going to put it up so that we can still see the code during the transformation. Okay, so this is the original AI module. And I'm able to get a block. And after I get a block, what I can do is I can do the original loop equals get loops of that block C. So effectively, this API is going to try to look at the block and trying to look up all the corresponding loops in here and unpack it. So it's going to give you an array. So I'm going to unpack it by this. Okay. And then actually I'm going to copy the schedule creation so that I will be able to run it, just run this code block alone. Yeah. Okay, let's see. So after we get the loops, what we can do is we can go and split it. So let's say I can do, I0, I1 equals sh dot split this loop of I, and the factor is, say, num4. Okay. And after I do this, I will be able to do s.mode.show. And you'll find that I'm going to get another loop in here, right? So effectively, what it's trying to do is to try to do a sequence transformations, and the result is being stored in this sch.mode member in here. Okay. So you'll find if I don't do anything, this is our original loop in here. And effectively in here, what we're doing is we're trying to split, right, this entire loop into two loops. You can find that, the original loop is being split by 32 by 4 in here. And the original axis mapping is still going to contain I, but now this t.x.spatial means that this I is going to be mapped onto I00 plus times 4 plus I01 times 1 in here. And that is my final result. So you're going to find that in this case, after this transformation, right, by running this transformation, we'll be able to get a different variance of program. And I can go ahead and try different things. For example, one of the things I can try is I can see if I change it to 8, you'll find that this effectively this loop iterator get changed, right? So if I run this program using different set of schedule transformations, I'm going to get a different variants of underlying program. This kind of transformation-driven language is very powerful because it allows us to effectively refactor the loop nest, right, by running those APIs without having to write the program. So imagine like how we normally would do such kind of code transformations. What you would normally do is you would just copy paste the code, right, and then do some of the manual refactoring, which can be very tedious. In this case, by having this, effectively program-based transformations, we'll be able to go ahead and transform the program different ways. So up till now, we'll talk about loop splitting. So there are other ways other than loop splitting. For example, one thing I can try to do is I can try to reorder the loop a bit in here. So after we split the loop, let's go to reorder this original program. To reorder it, we can find that well, it's the same order, but I can try to go ahead and do I1 and I0. Try again. And you can find that effectively the order of loops changes here. Right, so that's another way for us to be able to transform a program. Of course, there are other ways that we can go. For example, I could try to parallelize along certain dimensions by running sch.parallel.I0. Actually, I can do I1, outer loop dimension. To run that, you can find that effectively try to parallelize the outer loop dimension as an internal sequential loop. And here's the different part of original program. So what we take away here is that by having those pragmatic transformation APIs, we'll be able to take original program, right, and use these what we call scheduled transformation primitives to allow us to manipulate this loop nest in different ways. As a result, different loop nests can result in different performers, different performance code. And one of the ways that a lot of automatic program optimization doing is they will try to go ahead and try out different variants of program transformations, and then try to find the high performing ones among the set of choices out there. Okay. So we go through some of these transformations that we had before. Now let's start to think about the more complicated programs. Imagine that, hey, we want to do matrix multiplication. Okay. So in the case of matrix multiplication, one of the things that we want to do in here is let's try to define a matrix multiplication program first, and then trying to go ahead and build that vanilla matrix multiplication. Okay, so it can be a bit long, but let me walk you through each line here. So first of all, we're going to try to describe the matrix multiplication code as, we want to go into the reduction over K. There are two inputs, A, B as a placeholder, and the C's computation equals, AMK times EKM here. And we are going to iterate over, 1024 over 1024 over 1024. So if we go ahead and do that and trying to create the module in here, I'm going to try to create a given code block so we can clearly see what the code looks like in here. So if we go and do that, and we're going to create a function here, right, that contains A, B, and C as arguments. Okay, and I can do IR module show. So this is effectively a matrix multiplication program that contains A, B, and C as 3 arguments pre-allocated. And what I try to do is trying to iterate over 3 iterators, right? And then they will try to effectively map 3 iterators to M and K and run this iteration domain. Run this reduction. So this is a syntax called tensor. So there are some special meanings in this program. It effectively describes the reduction. So one of the things you might notice is that in this program, there's this called exit.remap, right? It effectively says that it effectively means M in here equals I0, N here equals I1, and K here equals I2. So it's just an assignment. But it also creates annotation. So this SSR means that the M and K are what we call spatial axes. So that they are effectively assigning corresponding to the locations of the A arrays, while the K here corresponds to what we call a reduction axis or reduce axis, because we are trying to accumulate over K. And in here, the T.init actually corresponds to the condition where effectively if we encounter this loop for the first time, it's going to initialize the corresponding locations using 0. Otherwise, it's going to do this accumulation operation here. So this is the IR module that we can create by running. This is what I call tensor expression domain-specific language that describes the matrix multiplication and creates a corresponding functions here. So after we have this tensor expression language and the corresponding functions, one of the things that we can do is we can try to go ahead and build it and try out the corresponding execution efficiencies. So we already have code to do it in here, so I'm just going to copy the code. So effectively, first of all, it's going to go and try to build the IR module in this line. After build it, we're going to create 3 arrays, right? We're going to create 2 random array of initialized by random numpy and a C array here. We could also try to go and confirm that if the implementation correct. So I'm going to create a numpy equals numpy.random here, b numpy equals then we're going to create a numpy a array and b numpy in here and C in here. Okay, and we can go ahead and invoke this. So we're going to invoke this array. It's going to store the result on the C, right? So we can try to compare c.numpy and a numpy, in this case amk times b numpy matrix multiplication. Okay, if you run this, you will be able to find that, well, it's a very small number. Most of the things are 0 because they are very close to each other. That means that, yes, it's indeed implementing things correctly. Another thing that we can do is we can try to call function.tom evaluator. And in this case, it's trying to evaluate, it will give me an evaluator that allows me to evaluate Tom. So I will be able to do evaluator A, B. I think there are other arguments to Tom evaluator. Okay, so that's a device. And number equals 3. So this means that we're going to run it 3 times, recall the averaging here. Okay. And let's try to print baseline from cost here. So it's going to take a bit of time to run the evaluation. And after it runs, you'll find that it will tell you effectively how long does it take to run this. I think in this case we have not do any transformation, right? So it takes about 3 seconds. So it's a unit of seconds. So you can find it takes about 3.71 seconds. Okay. So now we have this original program. Of course, one of the key things we can try to do is we can try to reorganize the loop a bit. Right, so in this case, I'm going to do a certain kind of optimization called tiling. So what you can do is you can first go and create a schedule. You get the surrounding loops. Right? So remember that I first get a block C, and then we'll be able to get the surrounding loops. In this case, if you look at the original code of IR module.show, the original code contains 3 surrounding loops, right? So I0, I1, and I2. I'm going to get block C in here. I'm going to rename them as YXK in here. And then I'm going to try to do a equally blocking. So effectively, I'm going to split the Y and X. I'm going to reorder it by YO, XO, K, Y, XI. So if you have learned about some of our previous lectures, might get familiar with, it's a bit like a register blocking in this case. If you run it, you can find that effectively we are splitting the loops, right? Now the loops become 5 loops instead of 4 loops. With this 2 outer loop and inner loop get split onto 2 loops component that get spread in outer and inner, and we'll still get the reduction dimension k in here. Okay, so we can try to go ahead and try and see, what are the possible speed up that you might get using this implementation. So you can go and build it again and run a time evaluator of time after transformations. You can find that in this case, by just splitting the loop a bit, we'll get quite decent speed up, right? You get a 3 point. By the way, this schedule.mode is the module after transformation. So you can find that we are reducing the overall running time from almost 3 seconds on to 0.37, 10 times faster than original computation. So that tells you, if you go and change your loop organizations a bit, right, you can get quite a bit of speed ups actually in this case. And another thing we can try to do is, maybe let's go and try different configurations in here and see what's going on. So let's see, I'm going to do define transform module. I'm going to get say tile y, tile x. Create a schedule, get a block, get the loops. Don't need this anymore. And I'm going to do tile y, tile x, the loop tilings, and return the transform module in here. So one thing we could do right in here is we can try to get mod equals transform the original IR module, the original parameter 32 by 32. And but we could try different arrays in here. So let's see, I'm going to build on this. It should be similar to the original one, given that we are just transforming the original modules by 32 by 32. Let's see. Oh, I just split it, but I didn't reorder it. So reorder yo xo k y I. Okay. You run this. Run it again. You can get 3.76, right? So what if I try to do it in 4 by 4? You're gonna get a different speed, right? It's kind of slower. So what if I'm gonna try to do it by 4 by 32? You can find that, depends on the ways we are going to change the iterations. It's going to give us different kind of execution speed. Right? Another thing that I can go and doing is on Colab. So I'm not sure if it's going to give me parallelism, but let me try. So if I'm going to parallelize it, well, it seems that parallel computing is not working in here because likely the Colab environment is only giving me a single virtual CPUs as opposed to many virtual CPUs. Okay. So anyway, so we will be able to run the code transformation, try out different configurations. Right? That gives us a different variants of programming here. And each variant of program is going to have an execution efficiency. So one very natural thing that people can try and do is people will be able to try out different variants of program configurations and then benchmark the execution efficiencies of each program variant and pick the best one. So that is effectively how most of the automated search framework works. So that allows you to be able to take the original program build a set of transformation that gives you, different variants of programs, run a benchmarking or a target environment, and use that to build a set of training data that helps you to predict the potential cost of a particular program configurations, and then use that potential cost to further narrow down a program candidates. Okay. So besides this, there are other optimizations that we don't have time to talk about, but if you're interested, you should go and check out this machine learning compilation course called moc.ai that contains more comprehensive tutorials on all the contents we learned about today, including the TensorIR and the set of transformations you will be able to do on top of this. Okay, so that is the loop level programs. How can we run the transformation API to build the loop level programs? Moving next, let's quickly look into what end-to-end model deployment might look like in a machine learning compilation. So in this case, we're going to use TVM's compilation module called Relay, and the first thing we're going to do is we're going to go ahead and download a ResNet 18 module from the Torch Vision library. And we're going to use Torch script to trace it onto a local variant. Then what we're going to do is we're going to also download the image we're going to use and run some of the pre-processing to be able to convert this image onto a torch tensor that we're going to use in here. And this is an image that we're going to use for our deployment workload. Okay. Once we have this, what we are going to do is, in fact, the first step is importing. So in Relay, there's a function called from PyTorch that allows us to be able to take a torch script module and a list of input shapes in here. And it's going to be able to give me a module that corresponds to the end-to-end neural network computation. So after we get the module, we'll be able to look at it. And you can find that effectively it corresponds to a sequence of operations such as, convolutions, Bayes-Torm, add, ReLU, and so on. So these are sequence of operations that we are going to use to implement a neural network. You can also find this sequence of operations contains quite a lot of the parameters, right? As these are input parameters onto this convolution neural network. Okay. So once we have this relay module, we can do, in this case, we're going to call a function called relay.build. That's going to build this computational graph. It's also going to go ahead and run all the process, lower some of the computations onto the loop program, run loop generations, which in our previous case, right, take some part of the computations and transform them onto libraries, and then also build an interpreter that allows us to be able to go ahead and run the corresponding and run an interpreter that allows us to interpret that final generated graph module. Okay. So after we get this library, what we can do is we can go and build a module called the graph executor. So in this case, the graph executor is going to give us a computational graph version that allows us to create, that allows us to do things like set input array, where this input array corresponds to the input image that we're going to use for prediction. Then we're going to call run that gives me that runs executions, and then finally you can do get output to run that, to get that output. Okay. Moving next, what we can do is we can try to see if the prediction matches what we are expecting. So in here, we are going to download the ImageNet SingNet that correspond to the class labels of each of the label class in here. We're going to obtain the ImageNet classes and then get the dictionary that correspond to class to ID. Okay. And then the output is going to be a 128 dimension vector in here. So we're going to take argmax that gets the class index, and then we're going to translate the class index to the key in here. And if you run it, you can find that prediction is tab ecat. If you look at the original image that we had in here, it indeed looks like a tab ecat, right? So that gives you a high-level overview of overall process of what it looks like in terms of running ML deployment through a machine learning compilation pipeline. Of course, there are more interesting things you can explore, such as what are the internals in terms of if we ingest the model, how do we run transformations, how do we map some of the computations onto the loop level program, and how do we automatically optimize those loop level programs. We don't have time to cover that in today's class. If you're interested, again, if you go to this website called moc.ai, moc.ai, there are additional materials about machine learning compilation that can help you to learn in a more organized fashion about this entire topic. Okay, so that is the end of today's lecture. Thanks everybody for coming and being with us throughout this amazing journey of building deep learning systems from scratch.